And then how X-rays are produced. And then the Compton effect. Bayer production, we already talked about that in chapter 37. And then there's something on the uncertainty principle, but not really want to spend too much time on that, because that's really from a separate topic, but I'll just mention it in passing. So I do want to talk about the photoelectric effect, and in chapter 38. Okay? So any questions though? If you have any questions for me? No? Good? Okay, add the scores on the cover sheet. I might have made a mistake when I added the numbers. And then let me know if there's something in there. So the photoelectric effect is about, well, the word photo is associated with light. Electric is with, an electric current, electrons, So the photoelectric effect is when you shine electromagnetic waves, if I can think of it that way, onto a metal. And then in the metal, there are, well, it's made up of atoms. The atoms have nuclei with electrons orbiting around those nuclei. And the electrons, inside the metal, they're, some of them are free, some of them are bound to go around the nuclei. But in the photoelectric effect, what was observed experimentally by Frank Hertz, 1887, I think is what I saw over there as the year, is you shine light, let's say, on a metal, and depending on the frequency of the light, electrons come off the metal. So there was like a certain value of frequency for the light shining on the metal. If the frequency of the light shining on the metal was higher than a particular value, and that particular value depended on the type of metal that it was. Was it a gold metal? Was it aluminum? Was it copper? So, depending on the type of metal, there's a particular frequency of interest. If the frequency of the light shining on the metal is higher than that frequency for that particular type of metal, then electrons will be ejected. If the frequency of the light was lower than that particular frequency for that metal, then electrons were not ejected. So photoelectric effect, it's related to light shining on a metal and then electrons being ejected from the metal. And so there were various observations made by the experiment conducted by Hertz. This is a guy whose last name is now used as the unit of frequency. So there were various observations, results that people observed experimentally, and it was basically the following. So here's the metal. Let's say this represents a metal, metal surface. You got vacuum above it. You shine light on it, and if the frequency of this light is too low, below a particular value, then electrons do not come off the metal. But if you make the frequency of the light shining on this metal higher, then electrons came off. And people were trying to figure out what was up with the result of this experiment. Because it was kind of puzzling. Because they, for example, like in this case, if they, for example, or if we go to this case over here, right? Oh, let's consider this case. Shine light on the metal, and electrons do not come off. So they thought, oh, well, in order for the electrons to come off the metal, you have to supply them with enough energy. So let's keep the same frequency of the light and increase the intensity of the light. intensity, you know, as you know, is the average energy per unit time per unit area. So people were thinking if we increase the intensity of the light but maintaining the same frequency, then we should be able to dump enough energy in there for the electrons to absorb them and then be able to be liberated from the metal. But when they conducted those experiments, for example, suppose this is a red beam of light. Suppose it's a red beam of light, just for the sake of argument. And then you shine this red light onto this metal and electrons do not come off. And then you still use red light, but you increase the intensity of it. I mean, you focus it, you know, but then they noticed that electrons were not emitted. So that was kind of weird, right? We made the light more intense, thinking we're providing more energy to the electrons, but then the electrons are not emitted from the metal. So why is that? On the other hand, if you consider this case, suppose that if you were to shine blue light onto the metal, electrons would be emitted. Okay, so then they thought, and when electrons were emitted, they could measure the energy with which they came out from the metal. So they figured, well, if we increase the intensity of the light onto this metal, we're putting in more energy, so therefore when the electrons come out, they're going to come out with more energy. So that's not what they observed. They observed that increasing the intensity of the light that of a particular frequency that caused electrons to come out, you still got electrons coming out, but not with more energy. What happened is that more electrons came out, as opposed to them coming out with more energy. So there was an issue over here with trying to explain what was going on. So let's say the cutoff frequency is, let's say, some particular value, right? In this case, the frequency of the light shining on the metal was lower than that, so electrons never came off. And they thought, let's make it more intense. That way, we'll be able to get electrons out. Make the beam more intense, electrons didn't come out. In this case, this is the frequency that will liberate electrons. Then you chose a frequency higher than that, and electrons came out the metal. But then increasing the intensity of that light that succeeded in ejecting electrons from the metal, people thought, well, we expect the electrons to come out with more energy because we dump more energy into the system, but that's not what they observed. What they observed is that more electrons came out. So it was a puzzle. And so the experiment was done, you know, since the late 1800s, and people were working on a theory to explain what was going on over here with this experimental results. And everyone failed because all of them were thinking of the light shining on the metal as a wave. You know, as an electric field amplitude, a magnetic field amplitude, which is what James Clerk Maxwell had, you know, discovered like 10, 15 years before that first experiment. And so they were, excuse me, treating the light as a wave, and they were getting nonsense, you know, results that didn't match experimental data. And this is where Einstein came in. Einstein came in, and in 1905, he said, I'm going to borrow that result from Max Planck. Max Planck in the year 1900 wrote this equation that the energy of a photon is proportional to the frequency of the photon, and the constant of proportionality became known as Planck's constant. So he wrote that equation. And so what Einstein said is essentially the following. He said, the reason why you guys are not able to explain what's really going on over here is because you're thinking of the light, treating the light as an electromagnetic wave, when you should be thinking of the light as a beam of particles, as a beam of photons, with each photon having this energy. So he borrowed this equation that was first written by Max Planck, and so Einstein used it, you know, in 1905 to explain the photoelectric effect. So he used this. So there was a little issue here because Isaac Newton, Newton died when? 1727, thereabouts. You know, more than, more than 100 years, more than 150 years before Einstein. Isaac Newton actually did a lot of work in optics. He actually discovered that white light is composed of all the different colors because he was able to get a couple of prisms, and so made for him by someone, and so he was able to shine light through one prism, disperse the colors into a rainbow, and then collect those colors again with another prism, and then make white light again. So he figured, oh, white light has to be composed of all of these different colors. So that was a success for Newton in the field of optics. But Newton claimed that light consisted of particles. So Newton thought that light consisted of particles, right? And he thought, if I remember correctly, that light traveled faster in water, for example, than in air. Turned out that that was wrong because light travels more slowly, in water than it does in air. But so Newton just thought, I think the light has to consist of particles. But that was, he died in 1727 or thereabouts. And then you have the rest of the 1700s, and throughout the entire 1800s, throughout the entire 19th century, people were conducting experiments with light going through single slits, double slits. Light was pretty much behaving as a wave. Diffraction, interference, they're all phenomena associated with waves. So throughout the entire 1800, the Young's double slit experiment, that was 1801. That was like 75 years after Newton died. And, throughout the entire 1800s, people became convinced that light was a wave and that Newton was wrong. And people just didn't know what type of a wave it was until James Clerk Maxwell came along into the picture in the 1860s. And he, was able to work with, what are known as the Maxwell's equations. And he says, oh, the electric fields produce, changing electric fields produce magnetic fields, and changing magnetic fields produce electric fields. And so light is really an electromagnetic wave. That's another story that I think I told you already some time ago. So, and, in the 1860s, with this work by James Clerk Maxwell on light, thinking of light as an electromagnetic wave. So then by the 1880s, 1890s, people said, oh, Newton was definitely wrong, right? He thought that light consisted of particles, and that was clearly wrong, right? All of these experiments show clearly that light behaves as a wave. And the theory of electromagnetism by James Clerk Maxwell and, some other people clearly shows that light is an electromagnetic wave. Right? So that was. But then people were trying to explain this experimental fact treating the light shining on the metal as a wave, and everyone was getting nonsense, right? And so Einstein said, I'm going to borrow this result from Max Planck. Max Planck, when he, came up with this formula over here, he was trying to understand, what the relationship is between the energy emitted from the surface of a metal and the temperature on the surface of the metal. And he had, there was data. And so he realized, he wrote a theory that would explain the energy emitted from the surface of a metal. Remember we wrote an intensity equation like this. The intensity emitted is like the emissivity times the Stefan-Boltzmann constant times the area of the surface from which the energy is emitted, and then times the Kelvin temperature raised to the 4th power. This is the temperature on the surface of the object whose area is A. So, he was working on this black body radiation problem, and he says, well, people, I can write a theory that explains the experimental data very, very well. The only fitting parameter is H, which became known as Planck's constant. And he says, but, when he wrote this theory, he says, if I think of the radiation emitted from the surface of an object as consisting of bundles of energy, then I get a good answer. But he says, I don't know why that happens or how that happens. It might be something about the mechanism by which light is emitted from the surface of objects, which I don't know about. So he attributed the, thinking of light or radiation emitted from the surface of an object as a beam of particles. He attributed that to some mechanism having to do, some unknown special mechanism having to do with the emission process. Albert Einstein, 5 years later, said, you know what? Forget about the emission process. Light is, by its nature, quantized into these bundles of energies, into these photons. And this is the energy of each one of those photons, as Planck told us, 5 years ago. And so Einstein made a lot of opposition, because they said, what? Are you saying that Newton was incorrect in saying that light consisted of particles? I mean, what about all those experiments throughout the 1800s, that show interference experiments, diffraction experiments, light going through a single slit, double slit, circular apertures, and so on, right? All of those interference patterns. I mean, light is definitely a wave. So, we can accept that something is going on with the emission process, but to claim that light by its own nature is quantized into these particles, you're wrong. But he used that way of thinking, that theory, to explain every single feature associated with the photoelectric effect. So it was like, it's like, I don't like how you did it, but you did it. Kind of, like, it's like, so he made a lot of opposition. Albert Einstein was, just defending that light was quantized into these particles of energy, right? And so, so the way he did it was as follows. Let me tell you roughly what's going on. How Einstein's theory of the photoelectric effect was able to explain every feature associated with what people saw experimentally. Okay, so first let's do this calculation. Help me out with your calculators. Consider a red beam of light. Consider a red beam of light. Well, let's go specifically to what was the wavelength of the diode laser that you used in the lab?
650.
650 nanometers, right? So that was 650 nanometers. So if I think of that light, that red light coming out of that diode laser, and I think of it as a stream of photons, what is the energy of each photon of that light? What's the energy of each photon? So the energy of each photon would be, I think for this class this is good. The energy of each photon is, I like to call it gamma for photon, right? So this would be HF. Now, what is the frequency of the light? If I think of it as a wave and the frequency is F, I can relate that to the wavelength like this, right? Now, this combination of Planck's constant multiplied by the speed of light in vacuum is a combination that shows up a lot. And it is useful to know that if you multiply Planck's constant by the speed of light, right, and you convert this to energy in electrovolts, and this is in nanometers. This is 1243 electrovolts times nanometers. I mean, from this expression over here, what must be the units of Hc? It would be an energy multiplied by a wavelength, right? Or some distance, right? It would be an energy, joules multiplied by meters. If you convert them joules to electrovolts, and if you convert the meters to nanometers, you get that number, okay? I mean, 1 electron volt, just so you know, 1 electron volt is 1.6 times 10 to the minus 19 joules, right? It's actually the charge of an electron. And 1 nanometer is 10 to the minus 9 meters, right? So if you use that. So, it's good to keep that in mind, right? It's very useful. So, for example, this is quite useful because if I want to know the energy of a photon of red light, where you think of the red light as a wave with wavelength 650 nanometers, then the energy of that photon would be 1243 electrovolts times nanometers divided by the wavelength in nanometers, which is 650 nanometers. That way the nanometers cancel, and I can tell you, or easily, quickly, without having to convert so many things, what the energy of the photon is in electronvolts. And what do you get? You should get something like around 1.6 or thereabouts. But, you know, do that and tell me what you get. That's if you consider a red beam of light of wavelength 650 nanometers.
1.91 electron volts? 1.91.
Okay, so 2 electron volts there. Okay, so let's say, okay, 1.91 electron volts, okay? For that particular wavelength. How about you do 1243 divided by 700? How much is 1,243 divided by 700? I guess that 1.6 that I was kind of quoting is more on the red end of the spectrum, not that particular wavelength. That wavelength.
1.78.
1.78? That's around 1.8 or 1.78. Okay, so that's what we get. Right? Now, what if you shine a, let's call this 1.90 for the sake of argument. What if you shine violet light? All right. So let's just say, let's go to the end of the spectrum, 400 nanometers. What is the energy of that? Photon. What is the energy of a photon of violet light? It would be hc over lambda. So that would be 1243 electron volts times nanometers divided by 400 nanometers. The nanometers cancel, and then you get the answer in electron volts. It should be somehow 3.2, 3.1, 3. Something around there is what. So, you know, for the visible spectrum, it's like from 1.7 to like 3.2, but this let's just make sure.
3.1. 3.11.
3.11, okay, so let's make it 3.1. Electron volts. Okay? Okay, so let's just keep those numbers in mind. All right? So we have, let's call this like violet, and I'm going to use this blue here, right? Okay. All right, so what if you have a metal? So this is a metal. This is a metal. Right? Oh, this is a metal here. And you have nuclei, I mean, you have atoms, electrons, and so on, right? Now, there is one parameter called the work function. So let me define what the work function is. I don't remember if it's phi or W, it depends on what textbook I'm using, and I just don't remember what, oh, it's phi. It's called phi here. I like to think of phi as an angle, but anyway. So there is this quantity called the work function. Phi, which is an energy. This is actually an energy. So what is the definition of that? What is meant by the work function of the metal? Okay, so this is the minimum energy, that an electron at the surface of this metal needs to absorb in order to leave the metal, be ejected from the metal, let's just say be ejected from the metal. So it's the minimum energy that the metal, that an electron at the surface, let's say an electron here, let's say that's an electron, needs to absorb in order to be ejected from the metal. So there are forces that bind the electron to the metal. Let me show you some values of work functions of different metals. Some typical values. Okay, so for aluminum, the work function is 4.3. For carbon, it's 5.0. For copper, it's 4.7. For gold, it's 5.1. For sodium, it's 2.7. For silver, it's 4.3. Silicon, 4.8, around, 2.5 to 5 or so electrovolts. Okay? I'm going to choose this one, 2.7, only because that lies between this and this. Okay? So I just want to base my discussion on this. So suppose this is a sodium metal. And the work function of it is, therefore, there's a table, and in electrovolts, the work function is 2.7. So what does that mean? That means that if an electron is at the surface of a sodium metal, if you supply that electron a minimum of 2.7 electron volts of energy, then the electron can leave the metal and be ejected from the metal. Okay? So if this is sodium, so I'll just write a little note over here for sodium. So Einstein said pretty much this. What if you shine red light onto this metal? So if you shine red light onto this metal, let's say with a wavelength of 650 nanometers, just to cite that diode laser as an example, you shine it onto a metal. When an electron here absorbs that red light, how much energy would it be absorbing? If you think of that as a photon, as a beam of photons, how much energy would it be absorbing?
1.9 electron volts.
1.9 electron volts. So when the electron absorbs 1.9 electron volts, will it cause an electron to leave the metal? When the electron needs at least 2.7 electron volts of energy to be liberated. So if you shine a red beam of light onto this sodium metal, electrons are just not going to come out of the metal. So Einstein said, no wonder you're not getting electrons out at that low frequency. Because if you think of this light not as a wave, but instead you think of it as a stream of photons. You have a photon here with energy, 1.9 electron volts. And then another photon in the beam, and another photon in the beam, and another photon in the beam. What happens is that these electrons, when they absorb these photons, when they absorb that energy, it's just not going to be enough. And he said, when you make the light brighter, remember making the light more intense, the way that you make the light brighter and thinking of them in terms of photons is you're just sending in more photons. But sending in more photons doesn't help, because each one of them is still a photon of red light, and each one of them has an energy of 1.9 electron volts. So therefore, no wonder you shine red light and of little intensity, and no electrons come out, because the energy of each photon, if they were to be absorbed by the electrons, is not going to be enough to liberate the electrons from the metal. And if you went to that other case where you said, well, let me increase the intensity. Well, increasing the intensity of the red light is still red light. You're just sending in more photons in the beam. But each photon still is a photon of red light, and each photon still has an energy of 1.9 electron volts, which is not enough to make electrons come off the metal. On the other hand, what if instead you shine, let me make this a little longer, still the same metal, just because I want more room. What if instead you shine blue light onto this metal? So we have blue light coming in. Maybe this is better. So imagine you shine blue light onto this metal. So So this is blue light. And let's say the wavelength of that is, well, I'll just take that value for the sake of argument. I don't have a violet marker, but we'll just a purple marker. I'll just use this one. So let's say 400 nanometers. And well, what would be the energy of, if I think of this light as a beam of photons, what is the energy of each photon? 3.1 electron volts, right? And if there is an electron here near the surface, would the absorption of this photon of blue light or violet light cause this electron to be emitted? So Einstein said, first of all, with these photons, either you absorb it or you don't absorb it. It's not like I'm going to absorb half the photon. No, it's all or nothing, right? And so if this electron in this metal, in the surface, absorbs this much energy, that's enough to make it come out of the metal. And so then what you would observe is that this photon would be gone, and then this electron would come off the metal. And Einstein said, well, when it comes off the metal, with what kinetic energy should it come out with? I mean, if this is the minimum energy, to make it come out, right, that's when the electron is going to have a maximum kinetic energy. And what should that energy be? What do you think?
1/2 mc? mc squared?
No, it's a particle, so you can't have.
Oh, okay.
No, but just do the argument. Someone is in jail. They need $2,700 to come out of jail. Someone comes along and gives that person $3,100. With how much money does that person come out of jail? Just the difference, right? It's like you pay this much to get out, and then you just have the leftover. So it's like this electron absorbs this much, 3.1 electron volts, but it's gonna pay the metal, 2.7 electron volts to get out. So what is that? 0.4 electron volts. So therefore, the maximum kinetic energy that this electron is going to come out with is 0.4 electron volts. And by the way, what happens if you increase the intensity of this light? Like what people did, right? Let's increase the intensity, let's see if the electrons come up with more energy. Well, no, if you increase the intensity of the light, you're just sending in more photons. But each photon is still a photon of blue light. So what will happen is that this photon, let's say that photon is going to cause that electron to be liberated. This photon, when absorbed, is going to cause that one to be liberated. This one is going to cause this electron to be liberated. But the energy balance for each electron is such that the maximum kinetic energy that they can have, is not going to exceed 4 electron volts. Maybe this electron needs not 2.7 electron volts of energy to get out because of what's around it. And so maybe it needs 3 electron volts of energy. But if you give it 3.1 electron volts, then maybe this one is going to come out with a kinetic energy of 0.1 electron volts. Right? But the maximum is going to be the difference between the energy of each photon of the light, right, and the work function. So Einstein wrote this energy balance equation. He says the energy of the photon coming in has to be equal to the work function. It's the minimum energy that the electron needs to get out, and whatever leftover energy will simply appear as the kinetic energy. And since this is the minimum energy, this would have to be the maximum kinetic energy of the electron. So he wrote this equation. So he wrote it like this: HF equals phi plus kinetic energy. That's the energy equation. So it's not a formula that I like to memorize. I just think of there's a photon coming in, an electron takes this photon energy, it uses some of that energy to get out of the metal, and the leftover energy is just going to appear as kinetic energy. That's how I think of it, and then it's not a formula that I have to memorize. If I think of the process, I can write down that formula every time I think about that process. And what's interesting is this, right? People had experimental data on, many different types of metals, gold, aluminum, different metals. And what they noticed was the following. If I solve for this kinetic energy here, that would be HF minus phi, right? So what they did was this. Can I erase this now? I think we don't need this anymore, right?
No, we don't need it.
Oh, 1.9 versus, I have the numbers over there, versus 3.1. Okay, so what people did then was the following. They had data for different frequencies of light shining on the metal. And so, you know, if you think of this equation like that, and they did a graph of the maximum kinetic energy plotted on the vertical axis, and the the frequency of the light shining on the metal, let's say hertz. What they noticed was the following. Let me ask you this question though, first. What would happen? Notice in this case, the energy of each photon is 1.9 electron volts, right? But the electron needs 2.7 electron volts to get out. So that didn't cause the electrons to come out. So the kinetic energy over here should be zero, because they just never even came out. In this case, the energy of the photon was 3.1, and since the minimum energy to get the electron out was 2.7, then they come out with 0.4 electron volts, right? But that was the maximum kinetic energy. What would happen if I sent in a photon and the energy of this photon is 2.7 electron volts? And here's an electron. Then it would take it, it would come out, but its kinetic energy would be zero. It's like, oh, I'm out. It's like giving someone money to come out of jail, but you just gave them the amount that they needed to get out. They came out pro. But they came out. So when people did a graph of the maximum kinetic energy with which the electrons came out, for various materials, they noticed this. The data was like this. You had a data point here, a data point there, a data point, a data point, a data point, and a data point, right? And by the way, what is the relationship between, notice how we do this in the lab all the time, right? We say, okay, we plotted this on the vertical axis, right? You know, like the y-axis. And we plotted the frequency on the x-axis, right? So that's this. And if I write this as a mathematical equation, what I have is y equals hx minus phi. And this is an equation of a line. With what slope? Planck's constant. And what about this? What is that? That's the work function. So the experimental data was like this. You know, it was like 2. But then there was nothing. Because if the frequency of the light is above this value, electrons come out and they have kinetic energy. But if the frequency of the light is less than this value, well, they just don't come out. So there's no kinetic energy. And kinetic energy can only be positive, right? So this over here is called the cutoff frequency, the threshold frequency. The cutoff frequency, the threshold frequency, is the frequency of this light that would correspond to a photon energy equal to this, so that the electrons come out with no kinetic energy. So this one would have a frequency equal to the cutoff frequency. F of C, I think, is what the symbol used. That's the cutoff frequency. And if you did a linear fit, right? And this is, let's say, if you did a linear fit like to that, this is, let's say, metal number 1. Whatever. Copper, silver, whatever, right? Notice that if you do a linear fit, right, this number over here, notice it's negative because you have a minus sign over here. So this would be minus 5. And so by just plotting the kinetic energy, the maximum kinetic energy with which the electrons come out, you can measure two things. You can measure the slope of this is Planck's constant. And the y-intercept is the work function. Well, with a minus sign, right? By the way, let's say they took data for a different kind of metal. Maybe this was copper and they did it for gold. Well, what you get is a set of points like this. And you do a linear fit, and it's exactly the same slope because it's Planck's constant. You can measure Planck's constant by just measuring the slope of that line. So this would be, let's say, for metal number 2. And then from the y-intercept, you can measure the work function of gold. And if you did another type of metal, you get data like this. You know, with the same inclination, right? Because you have Planck's, that's supposed to be Planck's constant. And so people, once Einstein wrote this, then they analyzed the data that they had, and they noticed, my goodness, all those lines have the same, they're all lines, and they all have the same slope, and it happens to be Planck's constant. And there's no data, you know, for frequencies below that cutoff. There's no data below that for that particular for those particular metals. So he was able to explain all the features obtained with the photoelectric effect. The thing that people were opposed to was, you know, light, it's a wave, you know. Yeah, you get good results over here if you think of it as a stream of particles, but it's a wave. You know, so there was a lot of opposition to, you know, they said something is right, but something is also wrong. Okay. So they were reluctant, but it explained every experimental data. And you don't need high-level mathematics for that. Look at the formula that I wrote down. It turns out to be like a line. Like this again. And conceptually, right? Conceptually, you got a photon coming in, the electron takes it. If it absorbs enough energy, at least the work function, it'll get out. If not, it's going to stay there, period. So like, you know, a technological application of this, you know, you have these solar cells, like in calculators, right? Some calculators, you don't buy batteries to charge the calculator. You just open up the flap in the calculator and you expose these solar cells to light. Light shines on those thin, you know, pieces of metal. Electrons come off, right? And then they become part of an electric circuit. And you know that's the current that you need for the calculator to work. So, and for this work, Einstein was awarded the Nobel Prize in Physics in 1921. So 1921, so Einstein was awarded the Nobel Prize.
Wait, I thought he never won it.
What's
he
that?
never won it for relativity?
Never.
Oh, okay.
Never won it for relativity. It was never given to him. Verifications of it came like he predicted the existence of gravitational waves. In 1915, they were first detected in 2015. And they don't give Nobel Prizes to people who have died. He was dead, he never got it.
So what if electrons keep coming off that metal? What will happen to that metal?
So what happens, you know, there's maybe there's a picture of a circuit that those electrons become part of. Like the question becomes also, how do you measure the kinetic energy with which they come out? So you have the right outside the surface of the metal is a vacuum, and then what you do is you near that metal, right? You put like another piece of metal that's positively charged, right? And then it attracts it, and then it makes it go. There's holes made in that metal, and then it goes through, and then you measure the voltage necessary to stop them. It's called the stopping potential. But let's see if I find a picture. I don't know if I included a picture in here of that's that. No, I guess I didn't. Oh, there it is. No, that's another one. No, I didn't include a picture of it. So this is what I was just telling you about. So in other words, they then accelerated those electrons through a potential, through a chunk of vacuum, and then they put a voltage across the metal from which the electrons came out, and the metals to which they arrived, and then they were able to play with the voltage to figure out what should be the voltage that would cause the electrons to become part of an electric circuit, and they measure the current in that electric circuit. And so they vary the voltage between the place where the electrons came off and the other voltage that they were, going towards, until the current went to zero. And if the current went to zero, essentially it's like this. Did you take to 80 already? So imagine you have this metal, or imagine you have this plate, right? And this is vacuum, right? And this is a positive plate, positively charged. And then you have and then this is negatively charged. Right? So you have a voltage between these guys. Right? And the electrons come out over here, right? And they come out with the maximum speed. That's when they have the maximum kinetic energy. And then, but the electrons are negatively charged particles, so they get repelled or attracted by this negatively charged plate. So will they speed up or slow down? They're coming this way. If they get repelled, if they are moving this way, but the force exerted by this is this way, the force will give them an acceleration that way. And if the acceleration is opposite the velocity, they'll slow down. So then they play with this voltage until these electrons would just barely make it over there. So like V final is the speed final is zero. So the kinetic energy over here, final, would be zero. So you just use conservation of energy. You say the initial energy is equal to the final energy. The energy is kinetic energy, plus, in this case, it's electrical potential energy. And then this is the final kinetic energy, plus the final electric potential energy. And they come out with maximum energy. The potential over here is, let's say, V plus, the potential of the positive terminal. The potential of this one is V negative. So the potential energy of a charged particle is Q times the potential, right? But the charge of an electron is negative. So it'll be plus minus E, and then this is the potential at the beginning, which is V plus. And then this is the kinetic energy at the end. So they regulate this voltage over here, so they stop when they get there. So this is zero. Plus, and then minus E times the final potential, which is V minus. This is V final. Capital V means potential, electric potential. Lowercase v means speed. So then you bring this term over to this side, and so the maximum kinetic energy equals E times V plus minus E, V minus, this is E, and then you factor that out. This is the charge of the electron, 1.6 times 10 to the minus 19. And this is that voltage. It's called the stopping potential. Because it's the potential difference between the plates that they move through to make them stop. It's called the stopping potential. Right, so normally you see this written like this, and it might even be in my notes over there. But I don't want to make too much of a deal of this because it's something that really comes in from physics 280, and many of you have not taken 280 yet. So this is E times that stopping potential. It's called, usually written like that. So essentially the question is, how do you measure this? So the electrons, when they come off the metal, you shine light over here, right? They come off the metal, and then you make them move towards another metal, and you make them slow down, and then you measure what the voltage should be over here. That will give you a zero, because when these electrons hit over here, they can become part of a circuit. So you measure the current over here, and when the current goes to zero, that's when the electrons are just getting there, you know. So it's related to something like that. When you take physics 280, then this is like, remember mechanical energy when you took 185, kinetic energy plus gravitational potential energy, right? So you just change the gravitational potential energy to electrical potential energy. And that electrical potential energy, in the case of gravitational potential energy, you can write that as mgh if the object is close to the surface of the Earth. So it's the mass times something else, right? But for electric potential energy, it's not the mass of the particle that matters, but the electric charge of it. And then instead of something else, it's something called potential. And a difference of two potentials is called voltage. But you learn about that when you take physics 2. Those of you when you take physics 280, but some of you have already taken it. All right, Einstein also wrote, from his theory of relativity. It's the same year, 1905, is when Einstein published this work on the photoelectric effect that won him the Nobel Prize. He also wrote down, in that same year, from his theory of relativity, expressions for energy. One of the expressions was this: E squared equals v squared, that's linear momentum, speed of light squared, plus the mass of the particle squared, speed of light raised to the 4th power. So he wrote this energy equation, right? And for photons, what do we get for photons? Well, for photons, we know that they travel at the speed c, because they're like photons, particles of light, but the mass is 0. So this term is 0. So the energy of a photon is just P times C. I mean, it would be E squared equals P squared C squared. Take the square root of both sides, and you get equals PC. But, so this was Einstein, right? Now, Max Planck had written that the energy of a photon in 1900, so this is Einstein in 1905. Max Planck in 1900 wrote E equals H times F. So if you combine those two, if you equate Planck's equation to Einstein's equation, you get PC equals HF. And if you divide by the speed of light c, you get h times the frequency over the speed. But if you think of light as a wave, the speed is the frequency multiplied by the wavelength, right? So therefore, f over c is just 1 over lambda. So the linear momentum of a photon is h over lambda. So this was Planck, and you can relate, h over lambda. This is a connection between the linear momentum of a photon and its wavelength. The shorter the wavelength of the photon, the more momentum it can deliver. So that's what these equations are about. How are X-rays produced? So let me tell you roughly what's going on with the production, with the generation of X-rays. So